You know this. We all know this. 1 plus 1 equals 2. It feels as solid as the ground beneath your feet. It's a truth you learn before you can even tie your own shoes. This simple equation is the first step on a grand staircase of knowledge. It is the bedrock upon which we build everything else. Our skyscrapers, our computers, our economies. All of it stands on this one, simple, unshakable fact. It's more than just numbers. It's a promise of certainty in a complex world. It's a universal language we could share with any mind anywhere in the cosmos. Or so we think. But what if it wasn't? What if, for a moment, we dared to question this absolute truth? Imagine a universe, just next door to our own, where 1 plus 1 does not equal 2. What would that place be like? Like trying to imagine a square circle or a silent sound. It feels like a violation of logic itself, a crack in the very foundation of reality. The thought is unsettling, even a little frightening. It suggests that the most basic thing we know might just be a local habit, a rule that only applies in our little corner of the cosmos. If we can't trust 1 plus 1 equals 2, what can we trust? The question sends ripples through everything we hold dear. It's not just about arithmetic anymore. It's about the nature of truth itself. If this pillar of certainty can be moved, then the entire temple of our understanding might come crashing down around us. The world as we know it, a world of predictable patterns and reliable laws, suddenly seems fragile. It becomes a house of cards, built on a rule that might not be as universal as we believed. This isn't just a game for mathematicians. It's a profound cosmic question. This single, tiny change, this one little crack in our certainty, opens a door to a vast and bewildering landscape of possibilities. It forces us to look at the world with new eyes. To understand how 1 plus 1 could equal something else, we need to pull back the curtain on mathematics. Math isn't just a collection of facts that have always existed, like ancient stones. Think of it more like a game. And like any game, it has rules. In mathematics, these fundamental rules are called axioms. An axiom is a starting point, a statement we accept as true without proof. They are the givens of the system. For example, a basic axiom might be, a thing is equal to itself. It seems obvious, but you have to start somewhere. From a small set of these axioms, we can build an entire universe of ideas. Every theorem, every proof, every complex equation, it's like planting a few seeds. From those seeds, a giant branching tree of knowledge can grow. If you change the seeds, you get a completely different tree. The logic can be just as sound, the reasoning just as rigorous, but the resulting mathematics will look entirely unfamiliar. The power lies not just in logic, but in the axioms you choose at the start. Imagine the game of chess. The rules are the axioms. A pawn moves forward one space. A bishop moves diagonally. A king moves one square in any direction. We accept these rules without question. From them, almost infinite games can unfold. But what if we changed one rule? What if pawns could move backward? Suddenly, the entire game is transformed. Old strategies fail. New possibilities emerge. The game is still chess, but it's a version from a parallel universe. It's just as logical, but follows a different path. This is the secret of mathematics. 1 plus 1, 2 isn't a law of nature handed down from the heavens. It's a conclusion that follows from axioms about what 1 means, what plus means, how numbers behave. These are the piano axioms, the rules for arithmetic we all play. They work wonderfully in our world, but they are still a choice. Mathematicians choose different axioms. They invent new games with new rules. Let's take a trip. We won't need a spaceship, just our imagination. In school, you learned a rule from the ancient Greek mathematician Euclid. He gave us the axioms for the geometry we all know and love. Flat surfaces. One consequence. Draw any triangle. The sum of its 3 angles is exactly 180 degrees. Always. Test it with a pencil and ruler on paper. It feels ironclad. Perfect. Predictable. Flat. But our world isn't flat. We live on a giant sphere, Earth. Let's try an experiment on this curved surface. Start at the North Pole. Walk straight down to the equator. Turn exactly 90 degrees to your right. Walk a quarter of the way around the world along the equator. Stop and turn 90 degrees to your right again. Walk straight back up to the North Pole. You've traced a massive triangle on the globe. What about its angles? You made two 90-degree turns plus the angle at the pole. The sum is not 180 degrees. It's 90 plus 90 plus the pole angle. Much more than 180. What broke? Did logic fail? No. We changed the game board from flat plane to curved surface. This is non-Euclidean geometry. It starts by changing one of Euclid's axioms, parallel lines. Tweak that rule and a new geometry appears. Angles of a triangle depend on size. Straight lines can meet more than once. This isn't just curiosity, it has real consequences. Einstein said gravity isn't a pulling force like Newton thought. Mass and energy bend the fabric of space-time. That bent geometry is not Euclidean. It's curved. Planets aren't being pulled. They follow the straightest path in curved reality. One changed axiom, one what if, revolutionized our view of the cosmos, from light bending to the birth of the universe. We've seen how changing the rules of geometry can bend the fabric of space. Now let's, get back to our original challenge. 1 plus 1. The arithmetic we use every day has its own set of comfortable, familiar rules. One of them is that order doesn't matter when you add. 3 plus 4 is the same as 4 plus 3. This is called the commutative property. It seems so basic, so obvious that we rarely even think about it. It's just how numbers work. What if a plus b was not the same as b plus a? This isn't just a wild fantasy. There are entire branches of mathematics built on this very idea. This is the world of non-commutative mathematics. Imagine that plus doesn't mean just combining quantities, but performing actions in a sequence. For example, let A be the action put on your socks, and B be the action put on your shoes. If you do A plus B, you put on your socks, then your shoes. Everything is fine. But if you try to do B plus A, you put on your shoes, then try to put on your socks. The result is completely different and a lot more awkward. Order matters. This kind of math isn't just a party trick. It's essential for describing the strange reality of the quantum world. In quantum mechanics, the particles that make up everything are slippery and uncertain. You can't know both the exact position and the exact momentum of a particle at the same time. Measuring one affects the other. If you measure position first, then momentum, you get a different result than if you measure momentum first, then position. The universe, at its most fundamental level, seems to be non-commutative. The math we needed to unlock the secrets of the atom had to break one of our simplest rules. And we can go even further. There's another rule we take for granted, the associative property. It says that how you group numbers doesn't matter. 2 plus 3 plus 4 is the same as 2 plus 3 plus 4. But what if it wasn't? In non-associative systems, the placement of parentheses becomes critical. The way you group your operations changes the answer completely. These mathematical structures are even more bizarre and harder to visualize, but they are being explored by physicists who suspect they might be needed to describe even deeper aspects of reality, perhaps related to string theory or quantum gravity. Our simple 1 plus 1 equals 2 is just one island in a vast ocean of possible arithmetics. So, we have these strange new forms of math. Non-Euclidean geometries, non-commutative algebras. Are they just clever inventions, abstract games for thinkers in ivory towers? Or do they tell us something profound about the universe we inhabit? The evidence suggests the latter. When Einstein needed a language to describe gravity as the curvature of spacetime, the tools were already there, waiting for him. Bernhard Riemann, a 19th-century mathematician, had already worked out the rules of curved geometries as a pure exercise of the mind. He was playing a game that turned out to be the rulebook for the cosmos. This relationship between abstract math and physical reality is one of the deepest mysteries in science. Why does our universe seem to play by mathematical rules? Why do mathematicians' games so often become the perfect language for the universe? It's as if the cosmos has a hidden mathematical blueprint, and we are slowly, piece by piece, learning to read it. But this raises a tantalizing question. If our physics depends on our math, what would a different physics look like? What kind of universe would obey the rules of a non-associative algebra? Imagine a universe where 1 plus 1 equals 3. Perhaps when two fundamental particles interact, they don't just bounce off each other. Maybe they merge and instantly create a third, entirely new particle, conserving some property we haven't even discovered yet. In such a universe, the very idea of counting objects might be flawed. Things might not be distinct and separate in the way we're used to. Instead of a world of billiard balls, it might be a world of merging watercolors, where combining two drops of paint creates not just a bigger drop, but a whole new color with new properties. Our technology is a direct product of our mathematics. The computer you're using right now, binary logic. The phone you're using right now, binary logic. It's a world built entirely on zeros and ones. 1 plus 0 equals 1. 1 plus 1 equals 1 0 in binary. The entire digital age is founded on the absolute reliability of these rules. Let's travel out among the stars, to a world orbiting a distant sun. On this world, life has evolved. A thinking, intelligent species has emerged. But they did not evolve on the plains of Africa. Their senses might be different. Perhaps they see using magnetic fields or hear through vibrations in the ground. Their bodies, their environment, their entire way of experiencing reality would be fundamentally different from our own. Why then should we assume that their way of thinking about the world, their mathematics, would be the same as ours? They might not even have fingers to count on. Imagine a species that perceives the world not as a collection of separate objects, but as a series of interconnected patterns like a vast, ever-shifting tapestry. For them, the concept of one, a single, discrete unit, might not be a natural starting point. Their mathematics might not begin with counting at all. Instead, it could be based on topology, the study of shapes and connections. Their version of addition might be about weaving two patterns together to create a new, more complex one. Their fundamental truth might not be 1 plus 1 equals 2, but something more like a line plus a loop creates a knot. If we were to ever meet such a species, communication would be the greatest challenge in history. How do you bridge that gap? We might send them a message containing the prime numbers, 1, 2, 3, 5, 7, 11, thinking it's a universal calling card of intelligence. But what if their mathematics doesn't have a concept of prime numbers? What if their system is not built on multiplication and division, but on transformations and symmetries? They might receive our message and see only meaningless noise. And we, in turn, might look at their elegant, pattern-based mathematics and dismiss it as mere art. The encounter would force us to confront our own biases. We tend to think of our logic and our math as universal, the only possible way to think correctly. But an alien intelligence could show us that ours is just one path up the mountain of knowledge. Their mathematics might be just as powerful, just as consistent, and just as useful for describing their reality as ours is for describing our own. It might even be better at explaining certain phenomena. Perhaps there are aspects of the cosmos, like dark matter, or the nature of consciousness, that remain mysterious to us, simply because we are using the wrong mathematical tools to look at them. This journey to the edge of certainty brings us to one of philosophy's great questions. Is mathematics discovered, or is it invented? If it's discovered, then mathematical truths, like 1 plus 1 equals 2, exist independently of human minds. They are woven into the fabric of the universe, timeless and absolute. We are like cosmic archaeologists, unearthing these truths one by one. Any intelligent species, anywhere, would eventually discover the same mathematics. 1 plus 1 would equal 2 for them too, even if they wrote it with different symbols. The universe has one set of rules, and math is the language we use to read them. But if mathematics is invented, then it is a product of the human mind. It's a powerful, creative language we constructed to make sense of the world. Like a language, it has grammar and rules we agree upon, but other languages with different grammars are possible. If so, our mathematics is not the only one. Alien minds could invent entirely different mathematical systems. Their tools would be just as valid. Their own science, their own technology, their own understanding of the cosmos. Perhaps the truth lies somewhere in between. Maybe the universe has an underlying structure, but more than one valid mathematical language can describe it. We can describe a sunset with a scientific equation about light, scattering a poem about its beauty, a painting of its colors. Maybe different mathematical systems capture different aspects of reality. Our math, based on counting and measuring, is incredibly good at describing the physical world. An alien, pattern-based math might better describe information flow or complex systems. This idea is humbling and exhilarating. It suggests our understanding is one chapter of a much larger book. There could be other chapters, in other mathematical languages, revealing parts of the cosmos we can't even dream of today. The universe might be stranger, richer, and more varied than our math allows us to imagine. The simple fact of 1 plus 1 equals 2 is the gateway to our universe. Other gateways built on other axioms may lead to entirely different realities. The universe is far stranger than our human-centric math can sometimes describe. What other fundamental assumptions might we be wrong about? Share your thoughts below, and if you want to keep questioning everything, subscribe for more mind-bending deep dives. If you enjoyed this journey into the unknown, hit that like button.